but I'm going to try to make a few points. And the speakers already have made many points that I can definitely relate to. And thank you so much for being able to be here. I have, in 36 years with IBM, have seen my company get close to high-performance computing and then go away from high-performance computing. And we, for many years, said that high-performance computing teaches us things about computer science that we could then use in the commercial world. And for many years, that wasn't really true. But with the convergence of analytics, deep learning, so-called artificial intelligence, it's more true than ever. So we're using technologies like MPI, and Jeffrey, I think remember you being a part of the original definition of MPI. So we're using MPI underneath distributed deep learning algorithms to accelerate them. We've talked for many years about hybrid computing models, and with our Power9 system, we now have coherent memory between the GPU memory and the CPU memory. And so for many years of computer science, we now see these things coming to fruition. When we first began to look at bringing flash technologies into commercial systems, we found that there's a no man's land between spinning disk and DRAM memory, 4 orders of magnitude of latency, and now all of a sudden we have technologies that are in the middle. We've had to invent new ways to get to non-DRAM memory that are faster than our conventional spinning rust. So the idea of cutting cycles out, so we have actually created another consortium, the Open CAPI consortium, to allow flash and accelerators to be attached more nearly into the computer system. So these days, we see a very strong coming together of these technologies, enabling what we believe is new science. And so when we talk about how big the disruption is, even world leaders are beginning to say, I've got to be a part of this or I'm going to be disrupted. So the talk that I give to our commercial customers is around, are you going to let someone disrupt you, or are you going to be the disruptor? Even our chairman talks about the incumbent disruptors. So it's really a pretty exciting time. I thought by this time, computing would be so mature that we wouldn't really have this level of innovation and excitement. And what we're seeing, though, is that these things are coming together, and it's actually more exciting than chasing spec int and spec float was back in the 90s, right? So when you think about disciplines, when I'm on the university campuses, I try to encourage people to realize that every discipline is being disrupted. When librarians can index books down to the chapter or to the sentence now, rather than traditional means of taxonomies, et cetera. We talk a lot about the breakthroughs in medicine and life science, the notion of classification and images and so forth. Our China research team has done a lot of work with what we call Power AI Vision, and I hope to get to show you some of that. This one was the one that really, we tend to think in the university setting about, the engineering teams, the computer science teams, and the hard sciences is very different from, say, the more literary side of the university. So when some journalists from NBC News started doing graph analytics, then we begin to see the relationships, new types of analytics, the Panama Papers, similar thing. So one of our partners, Neo4j, is one of the leading graph databases, was used in this story, and they basically put together the graph, and I apologize, I don't have a picture of their showing the graph, but you can look up on the Neo4j blog or on the Wired did an article on this. So even journalism now is using graph analytics or other analytics in the conveyance of their job. So what's going on? The end of Dennard scaling has caused us to think about, how do we continue to drive the economics of the industry? And it has resulted for us in what we call system level optimization. For many years, we were focused on, you know, how instructions flowed through the computer chip, the CPU chip. However, now we see that we must look at all layers of optimization, not just the computer chip alone. So what we have done is to open up our buses from the chip. It's NVLink with our partner NVIDIA. I mentioned OpenCAPI. We've gone hard after PCI Gen 4, first to market with PCI Gen 4, to enable an innovation ecosystem around the base computer chip. And so, you know, dealing with the new opportunities in light of constraints on our conventional system level optimization. Google announced back at our Open Power Summit about 3 weeks ago that Power 9 is deployed in their data centers. You know, so Amar Mahoney basically said, you know, Power 9 is Google strong, and they have now, you know, they like competition in the marketplace. We have that now deployed. You know, Oak Ridge is in the midst of acceptance testing on 4,700 Power 9 servers as a part of the Coral bid. So they would claim that the Summit machine will be the largest deep learning machine on the planet, right? With some 15,000 GPUs. And of course, you know, InfiniBand, et cetera, connections. So what's going on? You know, we used to optimize, like I said, you know, back in the, through the 90s and on, we were focused on optimizing, you know, database and web applications, or you know, actually early on it was just the presentation tier, but then became the web tier. Machine learning, of course, has been around. You know, I like to joke that some of our SPSS machine learning library members were written in Fortran, right? They wouldn't have written them in Fortran these days, right? So the vintage is, you know, some 30 to 40 years old, some of these codes. So machine learning has been around, but now with the advent of deep learning, graph analytics, geospatial analytics, other types of representations and insights, you know, natural language, et cetera, the notion that the way I can interact with the world, the way I can understand the world around me. What was interesting about the Neo4j example is that the Russian bots were not really detectable by what they looked like. They represented themselves well. But if you look at the context of who they were relating to and et cetera, you were able, that context was allowed the journalists to show that, no, these are not real people. What this is saying is that the analytics is countering our intuition, right? So we as humans basically say, well, I trust this person, I'm gonna get my news from this person, or I'm gonna try to read the text and detect whether it's real or not real. Turns out analytics brings in different insights that are able to tell better than the human. So here's what I see happening. This is from a more commercial space. Most companies have invested heavily in data lakes. The modernization of the data, you know, time series graph, object store, the notion of text analytics. So, you know, back in the day, we would have just put new capabilities into relational database, but now we see with our partners, there's just an explosion of data stores augmenting the traditional relational database store for analytics. Unstructured data, of course, many people said, well, let's go collect the data and we'll figure out what to do with it later. So we end up with sort of the data swamp here. So what we're in the era now of, can we make that data productive, right? Are we able to gain insight from this data that I have churned out? Some telecommunications companies have, you know, tens of petabytes of data. You know, when the data lake ate the data center type of relationship to the data lake. We're rethinking big data, right? The fact that I have more data isn't an advantage. What's an advantage is can I bring insight to it. So the new thing that I see emerging is the data science workbench, which is increasingly Python oriented, and we'll talk about that, and what I will call the AI grid. It's the AI grid that looks like an HPC cluster, you know, Rocky Ethernet or InfiniBand, high-performance compute, very fast ephemeral storage, flash or SSD storage. So this is a traditional, scheduler-based compute environment supporting the analytics. It's a very different optimization point from a data lake, for example, which is optimized for cheap and deep storage, right? Dollars per petabyte. The enterprise data warehouses were optimized or are optimized around dollars per gigabyte per second. So this is for the first time the emergence across many industries, finance, telecommunications, and others, the need for a platform which looks just like HPC. From an optimization point. So many of the lessons we've learned over the years are coming to bear for our commercial friends. I'm going to skip through there. So like I mentioned, we've opened up the buses, OpenCAPI, NVLink, PCI Gen 4. This creates opportunities for research with our Open Power Consortium that's now over 320 members. Many universities, we should talk about the academic discussion group, very active, some 100 universities or so are part of that within our Open Power Foundation, talking about how we bring value and do research. We now have what we call the Power Inference Engine, which is able to push a trained deep learning model into an FPGA so that for a mobile device or for an automobile or whatever, an embedded device, I can now push the analytic scoring or inferencing out into the edge. So the notion of moving the data, so there's been a lot of debate over the last few years about, do I bring the compute to the data or the data to the compute? And the answer is yes, at all levels. It's really about, can I feed the beast, right? So can I move the data at the right speed? So memory bandwidth, IOPS to memory, cache sizes, IO bandwidth, getting to the accelerators with open band, with high bandwidth really is the answer to winning in the analytics space. So that's what leads us to this notion that I really have to think through the stack, all the way from Python down to libraries and CUDA, et cetera, down into how the bits are wiggling. The typical data scientist doesn't care, what hardware he's running on or she's running on. They don't care how the bits are wiggling. What matters is, can I get to innovation faster? Can I go disrupt someone else more quickly? Can I spin through training? So in some cases, we see training go from days to hours in this enablement. I'll talk about the data platform, but let me give you just a clue on the workbench. This is what we see emerging both in the university and in the commercial space, the idea of how I can now create a workflow that is tailored for the type of analytics. Would be different for image than for natural language. If I'm doing a graph relational analysis, it'd be different, and so forth. So can I build an ad hoc workflow that leverages the underlying technologies and sources the underlying data? So it's about, of course, the workflow and the data flow, building that out. And just to give you a sense of the diversity, I mentioned before, so streaming, natural language, image, graph, geospatial, these are things that were kind of niche plays before, but now, trucking companies are talking to Google, right, for geospatial and logistics types of things. So the relationships, I have a professor colleague at NC State, North Carolina State. He teaches MBA students how to do analytics. And the first thing he teaches them is how to think. And a third of his students hate him. A third of his students say, hey, these are great tools. I'm going to go apply it to other things. So it changes even the business student in the way in which they approach the world. So I'm going to share a couple of partners. So Anaconda is a startup in Austin that has the leading distribution of Python. So we partnered with them for the Python ecosystem. So the Anaconda distribution has machine learning, data connectors, distribution, numerical libraries. So this world of, 20 years ago, we were really optimizing around math libraries that were generally proprietary. Now it's about open BLAS and being able to interact with that open source ecosystem. So being able to take our optimizations, getting them into the community, get them into the supply chain of the capabilities. So the value of Anaconda to us is that it provides a packaging model and a detangling of the hundreds of dependencies. So in this world, I compose software rather than write software alone, right? So I bring in all these parts and I began to be able to create a new project from them. IBM has some similar thing around the data science workbench. We call it DSX. It's a microservices, Kubernetes-based, Docker-based enabler. Also brings things like security and multi-user capability, but it's still Jupyter Notebook-based, Python-based types of analytic capability. Another startup who has an open source component is called H2O. They have something called the driverless AI. And the reason they're kind of interesting is they have a slider GUI-based interaction with machine learning. So for traditional machine learning, you can dial in explainability of the model, for example. And so it does two things. One is productivity. The other is lowering the bar for access to machine learning capabilities. So, an engineer could pick this up and not have to, spend his dissertation on doing the underlying math, right? We see universities beginning to pick up these technologies at Michigan. We see the use of machine learning to make more efficient decisions around adaptive grid for computational fluid dynamics simulation, for example. We've had adaptive grids, but now let's make them smarter for advanced computation. So what IBM is now doing is we're putting out our own versions of some of the deep learning frameworks. So open source and then proprietary value add. MPI is one of the examples of a technology we leverage. So things like TensorFlow, Caffe, Chainer are a part of this distribution, and then we'll do the underlying optimization as the model moves forward. So it's a pretty broad platform. You can see there's a lot of partners in here. Let me get you to this one example, and then I think, I don't know how I'm doing on time, but this example shows that if I do a distributed deep learning across the number of computers, leveraging the sum-reduce collective ops, as well as the low latency interconnect, I can now take and spend more spins on the model through the distributed training than I would have done before. So the prior example was 9 days, GPU accelerate with power, with a high bandwidth, high bandwidth to the GPU, high bandwidth among the computers, so that at the edges I can, share the data for the back calculation. So the overall data flow looks a little like this. The GPU to CPU memory, InfiniBand through the switch, etc. So this is an overall system optimization. Sorry, I'm getting dry here. I have a water in the back right there. Thanks, Craig. Sorry. It's cold weather. So if I'm not mistaken, this would look a lot like what we would have drawn for an HPC grid back in the day, right? So here's an example, distributed deep learning, back to Amdahl scaling, right? And so because of the efficiency of the scaling of the underlying technology, I think we're within a few percent of, this is scaling up to 256 GPUs or 64 computers using that type of technology. Another one is what we call large model support. So when the model itself exceeds the size of GPU memory, I'd like to be able to not fall off, right? So traditional GPU attachment has been with PCI Gen 3, 16 gigabytes a second. But what happens when I get 50 or 60 gigabytes a second to the memory, and you can see that, you know, in the time, in the same time I can get, you know, one iteration done, I can now get, you know, 3.5 or 3.8 or something done. So the need for larger models is driving us to leverage that bandwidth of moving the data in and out of the GPU core memory. That's where our collaboration with them has driven this coherent memory between GPU and CPU. So we also see, similar to H2O, we see the emergence of tools like this, which are about the productivity of training these models. So we have a component called the deep learning impact, which helps you see, is this training, you know, on track or off track, so I can kill it early or modify the model without having to without having to wait days or hours for it to complete. So this idea of productivity, can I get to the science faster? Can I get to insights faster? So things like, you know, underfitting, overfitting, you know, divergence, et cetera, are modeled and monitored in progress as it loops through the iterations. And then finally, computer vision. So the ability to drive more quickly image classification, whether it's of cars, you know, autonomous driving or safer cities or whatever, radiology. We're seeing the ability to, with this tool, the ability to train a simple model, score that model, make a better model, et cetera, iteratively saves the time required to draw boxes around, you know, 1,000 objects for classification. This was actually developed by our China research team. They're just outside of Beijing. And then finally, you know, we use spectrum computing. The idea of LSF back in the day, right, now can support Spark, you know, so the convergence of this compute with Docker has happened much faster than I expected. I thought, you know, even HPC going into Docker world is not something I really expected, but unlike virtualization, container technology has gone very quickly. And so that notion of a grid to run this creates complete sort of the story for the overall emergence of this analytic platform. Judy, I don't know how I did on time. But
no, you're ahead of time.
Oh, well, I can talk some more.
Yeah. So maybe if we could ask some questions here.
First of all, it was a great talk. A couple of things struck me. First is more intended as a light comment. First talk I've heard about AI and IBM in a long time. I never heard Watson mentioned. That's okay.
That's refreshing.
Yeah, that's right. The other thing I noticed, there was a lot of places in your deck where you talked about Hadoop, and I presume HDFS is really underlying things. Isn't that technology getting a bit old now? I would assume that you guys moved on to something better than that.
Actually, we partner with Hortonworks, so the data lake itself. There's a bit of a, if I might go back, there's a bit of a debate about where this AI is going. I showed you a story where we're going to augment the data lake with this compute grid. We're going to demonstrate with Hortonworks, we're going to demonstrate with Hortonworks that we can, so Yarn Hadoop 3 supports pools and Docker. So we're going to put Power AI deep learning in the lake. Now, I personally believe that, you know, Hadoop is really, you know, 25 software components flying in close formation, right? It's it's a fairly complex beast. And Spark is a better in memory for, acyclic graphs computation. But people are so invested in these things. It's going to take them a while to go away. It is nice to be able to, as they say, schema on read instead of schema on write, have that diversity of places. So what I think is happening is Hadoop is becoming the place where you land the data, you might do some manipulation, visualization, exploration, but I don't think it's a great compute platform. It's more of a storage, cheap and deep platform. It's kind of the way I'm seeing it, right? So Hortonworks is invested, and the other the other providers, MapR and Cloudera, are all investing in data science on the lake. So Cloudera has they want to be the hub, so they have the data science workbench on the Cloudera thing, and they don't even use the term big data anymore. They are on to the next hype term, right? Around the data science, but that's a very keen observation. So it seems like HDFS is probably going to be around as a storage element. We've actually created within GPFS, now called Spectrum Scale, a data transparency layer, so we can put our storage underneath the data lake. 1.3 copies instead of 3 copies of data, we think is cheaper, right? So using erasure coding, we can actually optimize that further. So I'm of a mindset that, the people who built these thought this was going to go away. Well, that didn't happen. and the Hadoop guys initially thought, well, we're not going to have any of these other modern databases. It'll all be here. So seems like what's happening is we're just augmenting. I don't know what goes over here, but off to the right. But for now, anyway, we'll see. Another 2 years, we might have a different story. Any other comments?
I have one more.
Yes, sir.
I was intrigued by what you were saying about FPGA and mapping trained models to a single FPGA or to
Can you just repeat the question? Because
Gotcha.
Oh, sorry. I can say it loud.
Yeah.
So, anyway, one of the things that Microsoft has done over the last couple of years, Doug Berger there did this whole mesh FPGAs to do a lot of model work. And I was intrigued that you're looking at it from a single FPGA. Now that you can map the whole trained model.
So the question was about FPGAs and mapping to a single model versus multiple FPGAs. What we've done so far, well, let me back up. The challenge with FPGAs has been, I need a hardware designer to implement. And so trying to get programmers to work with FPGAs has been hard, and we've tried. We had a research project to try to, make C map to FPGAs, and we're not working on that anymore. Just say that. So what this is, again, it's from our China research team, is they came up with a way to do the underlying software so that if I have a trained deep learning model, I can push the scoring or the inferencing into the FPGA. At this point, I don't think we push it across multiple FPGAs, but that may be a statement of time. And so, Intel, spent $17 billion on Altera, so that Microsoft had something to do with that, I think. However, Xilinx is our partner, has a very significant market in the embedded space. So one of the areas that I'm trying to work with telecommunications companies and others on is this idea of distributed analytics. What if I need a consistent data view across, the edge or the endpoint, the edge, the regional, the mothership analytics? What's that look like? So I think we're seeing some technologies emerge, especially around the IoT, industrial IoT, that kind of stuff emerged there. So I think FPGAs will have a role, but it's not the general case. The general case just proved to be too hard for us. Yes, sir.
Yeah, we have a collaboration at our Dartmouth lab with Hartree, with IBM, and IBM Research, and looking at what they call cognitive systems. I used to use the word AI, yes. But I'm slightly puzzled in the context of cognitive systems that you haven't mentioned Watson at all. Well,
I'm from the part that's called cognitive systems. I can talk to Watson. So Watson is a big part of, a major part of our line of business. Because of the nature of what we're doing here, I focus more on the implement and design and build. Right, and so absolutely, we have a number of collaborations with the Watson team. One of the challenges I have in talking about Watson is it's a brand, it's a set of software, and so it manifests as different things, right? We seem to do that to ourselves repeatedly. We take a name, this is really a good name, let's use it for everything. So Watson is a basic AI technology, is a pipeline where we tend to deliver it as a cloud service, so there's a service up front. What this is for people who want to build their own. So you can start incrementally and if you do just a piece of it. So in that sense, this is very complementary to Watson. The Watson service, we have some folks in regulated industries, for example, who don't want their data in the cloud, or they can't get it past the auditors in the cloud. So we see actually both ends of the spectrum. So that was one of the reasons I didn't really mention the Watson thing. And absolutely, at the Hartree Center, I read about you guys and the work you're doing is really cool stuff. So maybe we can follow up a little bit there. Yes, sir.
So I have a question. You did a good job talking about HPC and AI and how, in many ways, the hardware that's underlying these are coming together. That's both exciting and scary for some of the HPC computer architects. And the scary part is that people are worried that double precision floating point is going to go away. Do you see any of that in, because the AI has less requirements for floating point than traditional HPC simulations do. Do you see any of that at IBM? Do you have any forecasts for, should we expect single precision, half precision, and have to live with this, or?
I don't see it going away. I do see, I have tracked accelerators for many years, and before the end of Dennard scaling, creating an effective accelerator that had any longevity was hard, right? However, the advent of these, TPU from Google, tensor processing units, I think within the GPU and within these specialized units, you'll see, more focus on the single precision types of stuff. For general purpose compute, we don't have any plans to back off on double precision, within the core CPU or whatever. So I think, yeah, things move slowly. If that happens, it would take a long time. Yeah. Yeah, I can't get my head around that happening. Sorry, the question was, does double precision floating point go away with the advent of this deep learning single precision or less types of math? And the answer is, I don't think so. I don't think it goes away.
Okay, excellent.
Okay.
So, let's thank Linton. The next speaker is Nathan.